All right. Good morning, everyone. This is a talk that some of you might have already seen a variant of, because I've now done it in Chicago and in New York. However, I want everybody to pay attention. I've added some bonus content. Now contains fun bonus facts. Not all facts guaranteed to be fun. So this is a talk about compilers, and the first part of the talk tries to be kind of general and teach about compilers in general. And the second part talks more specifically about how that applies to Ember and where we're taking Ember. Compilers do have a reputation of being a bit scary and a bit difficult. If you studied computing in university, the compiler course often has a reputation of being the hard one. Or if you got directly into web development, hands-on training or a boot camp, maybe you didn't talk about compilers at all. And it's true that making a brand new compiler from scratch is a big job, and making a great one is really hard. But just understanding more about what they are, what they can do, what they can't do, is very empowering. And I want people to not be scared of compilers. There's a lot you can do just by understanding the basics. So with that, we'll launch into it. We'll start with a bonus fact, however. So I live in the Commonwealth of Massachusetts. Massachusetts was founded in the year 1630 by Puritans. And the Puritans were basically the 17th century equivalent of the Taliban. They were not nice people at all. They were so unpleasant that the celebration of Christmas was illegal in Massachusetts from the year 1659 to 1681. Things have changed a little bit in Massachusetts since then. Now it's quite a progressive state. It was actually only the sixth jurisdiction in the world to legalize same-sex marriage in 2004. Behind only the Netherlands, Belgium, and 3 Canadian provinces. Ahead of Denmark and Sweden and Norway, actually. So, what is a compiler? The word compiler was coined around 1950 by Grace Hopper. And by 1952, she had a working compiler. But she had to work really hard to convince people it was even a good idea. That it was desirable and possible were both things that people didn't really believe. She had to invent and explain in excruciating detail how programming could work. This is a diagram from a paper she wrote, and I just find it really fun that she had to write a box and say, brain goes here. Because she's really trying to explain the division of labor, a new division of labor between the person and the computer, and how compilers would radically alter that. Right? Because the point of it was to move work onto the computer that before humans had to do by themselves. And she had to invent a lot of concepts from scratch that we recognize today still, and she just had to come up with them and come up with names for them and try to explain to people what they were. Right? The idea of having API docs, of having libraries, of a distinction between source code and machine code, these are things she had to come up with. So next bonus fact, she did some of her early work at Harvard University, which is about a 2-kilometer bike ride from my house. Harvard was founded in 1636, and if you happened to earn $200,000 every day since 1636, you would still have less money than Harvard. They are very rich. It's about $37 billion endowment right now. Yeah. So what is a compiler? We're back to. A compiler is a program. And of course, when we talk about programs, most of us in our daily work don't sit down and say, I'm going to write a program today. What constitutes a program kind of depends on your frame of reference. From the perspective of your operating system, you probably spend all your time in a program called Chrome or Safari or something like that and makes tiny changes within it. But of course, from the perspective of the web browser, your Ember app is a program. But every program we can talk about has an input and an output. Right? A program is just a set of instructions that takes some input and produces some output. What does this mean for an Ember app? Well, your input, it starts with a URL, and you get a stream of events from users, and your output is HTML. Right? We understand that. That's what I mean by a program and its input and its output. Well, so a compiler is just also a program, just another program. And the difference is its input and its output are also programs. Right? And this is where we begin to get into the somewhat recursiveness of compilers that makes them sound a little intimidating. But when we say a compiler takes a program as input, we don't mean any one particular program, of course. That would be a pretty boring compiler. What we mean is any program in a particular language, which I'm just going to call language A, as your input. And of course, the output to be useful, needs to be in some consistent language too. So we'll call that language B. And then there's one more language missing on this diagram because, of course, the compiler itself is written in some language, right? So we have 3 languages here. And so this I've just given you is a very broad definition of compiler. I think it's the most useful definition of compiler. Some people might quibble and try to be more precise about what they consider a compiler. Some people would say a true compiler is one where the input language is easier for humans and the output language is easier for machines. Or you might say a decompiler is the opposite of that. It takes a machine language and tries to translate it back to a human language. A self-hosting compiler is one where the input language and the compiler's written language are nearly the same, right? And so these are also called a bootstrapping compiler because it means that the compiler can compile itself. And a transpiler is just a compiler where the input language and output language are kind of the same language, nearly the same language. All of these, I'm highlighting them mostly so you know how these terms fit with the concepts. I don't actually think the distinctions are very important and they're very subjective. Is Babel a true compiler or a transpiler? Depends on your opinion. Is ES 2019 the same language as ES5? If they're the same language, it's a transpiler. If you think of them as different languages, it's a true compiler. Not a very interesting distinction, I think. But people argue with these terms, so I think it's good to define them. All right. Bonus fact time. I live in the city of Somerville. It borders 2 more famous neighbors, Cambridge and Boston. Somerville is only about 11 square kilometers with a population of 80,000 people. This makes it the densest city in New England, and it's denser than Boston, and even denser than Copenhagen. The name Somerville was chosen for no reason whatsoever. When it split off from Charlestown in 1842, a committee of citizens just thought the name sounded pretty and picked it. I'll also add that the creator of the webcomic XKCD lives in Somerville. We have a lot of cool people there. In fact, we have approximately 2 Ember core team members. I say approximately because Jen is like right on the border. So, what can compilers do and not do? And this is important because it also helps us define what compilers are. Because to be a good compiler, there's an important thing a compiler has to do. So we said that our output of our compiler is a program. And we said that all programs have input and output. So we can also think about it like this. Right? Our output program is going to have an input and an output. And the thing to notice here is that the output program has to work for all valid inputs, and the compiler can't see them all in advance. It can't know what they're going to be. The compiler can't see the inputs that are going to be given to the output program. And so the compiler can't run the program. Right? It doesn't have enough information. The program's going to have to run many times with different inputs. And so there's a lot of things the compiler can't know about the state of the program. We say that those things are dynamic, that the things that you can't know till you run the program are dynamic facts. The things that you can know without running the program are static facts. Right? These words, static and dynamic, are very, very useful in programming, so they tend to get overloaded to mean a couple different but related things. In this talk, I'm going to use them specifically to mean this, to mean facts that you can know about a program before you run it, or facts that you can't know until you run it. Right? So compilers only know the static things about a program. So anyway, since our input is also a program, and all programs have input and output, we can also think about it like this. There is a way to think about our input program, accepting input and having output. And this takes us to this takes us to where I was going with it, the important fact about compilers, because to be a good compiler, if the inputs are the same on each side of this diagram, the output should definitely be the same too. Right? The point is that a compiler doesn't change the meaning of its input. It preserves the semantics of the language. Right? So it can change the performance. It can change what environments the program is capable of running in. It can change what hardware it runs on. But it doesn't change the meaning of the program. You should still get the same meaning. Otherwise, it's not a compiler we're talking about anymore. It's something different. So an important idea to take away from this is that this red arrow down here, going directly from the input language to the output, is often unimplemented. Right? If you've ever worked in C or Java or Rust or Go, any of these compiled languages, you're familiar with the idea that if you have some input program Before you can actually get any kind of output, you have to compile it, get an executable, run that, and get the output, right? Just as an example. And your Ember app is the same way, right? The files that you author, router.js, app templates, application, HPS, those files are not things that the web browser can do anything with by itself, right? They're not really runnable. And so before you can actually get anything done, you have to run your Ember app through the compiler, which is Ember CLI, to get a compiled output that goes in a folder called dist, and then that's what can actually run to produce the output of HTML on the screen. So that's what I mean by saying that this extra arrow here is unimplemented. But I want to make the point that it's not, just because it's unimplemented and the output of the input program is effectively imaginary, doesn't mean it's not important, and doesn't mean it's not important to think about when we do design. What I mean by that is, the way it really works is something like this, right? You know that in order to get all the way to the output, to get from an input to an output, your app has to be compiled, and then we actually run the compiled output, and we go this long chain of events, as on this diagram. Because you know that's how it really works, you might be tempted to think about the designer system in those terms. But it's really much better to be able to think about the system like this, right? We really want users of Ember to be able to think in Ember, right? And the same is true for any input language. You really want the users of your language to think in the language and think about what it means and what a given input should produce as a given output, without having to think about how the compiler works, without having to think about what the compiled output is, how it works on its given platform, right? And so this all comes down to a clean distinction between implementation and interface. So I'm going to call, forgetting to do this, I'm going to call the implementer's trap. Because it's very tempting when you're the implementer and you know how it really works to forget to think about your abstract semantics, to let the details of the implementation sneak into the meaning of the language, right? And you don't want to do that. It causes two big problems. One is that it makes life harder for readers of this language because there's just, if there's not a clear definition of what something in the language means, independent of the implementation, they have to go learn the implementation to understand what it means. And the second problem is it makes it much harder to change and improve your implementation when the meanings are tied to the implementation, right? So this lesson applies to much more than just languages and compilers. Anytime you're designing API that other programmers are going to use, thinking clearly about the difference between the external interface and what it means versus the implementation, having that boundary is one of the key skills we develop as developers when we're trying to make good APIs and good systems. So, bonus fact time. Lego blocks are famously invented here in Denmark, but you probably don't know that Somerville has our very own life-sized Lego giraffe. Because we have our own Lego Discovery Center, and it's in a newly redeveloped neighborhood called Assembly Row. And it's called Assembly Row because it was formerly the site of a very large car assembly factory where Ford assembled their Edsel line of cars. And the Edsel was famously such a disaster. It was so overhyped and so underdelivered that the name Edsel became a synonym for failure of products for years and years afterward. So that factory closed in 1958, and it contributed to a period of significant decline in Somerville for many decades. So moving back onto our implementer's trap, do we have this problem in Ember? Like, where do we make this mistake? Does Ember have clear abstract semantics? The answer is overwhelmingly yes. Overwhelmingly we get this right in almost all places. And the reason we get it right is because we follow web standards for many things, right? In Ember, HTML means what it's supposed to mean in the specs. JavaScript means what it's supposed to mean in the specs. And when I say that, that's another way of saying that the meaning of that code is defined by the abstract specification and not by the particular implementation, right? Your JavaScript means the same thing on Chrome and on Firefox, hopefully most of the time. Your HTML means the same thing in all those places. And so we have good separation between interface and implementation. And the other area is that Ember's own APIs are pretty carefully designed to provide that separation, to make it possible for us to do things like swap out the implementations, things like replacing our rendering engine. We've gone through like 3 or 4 generations of rendering engine, changing the implementation underneath you, without breaking the semantics because we had good, clear meanings of what the templates meant. right? So we do it good in almost all areas, but there's an area where we're weak, and that is the use of modules. So Ember was a very early adopter of module syntax in JavaScript, which turns out to be very good for us because the vast majority of code that we have out there in the ecosystem is written as modules. And Ember people even helped write the standard for modules, and we were part of that process. And feedback from Ember helped shape the spec itself. But we haven't fully adopted their semantics. And I'm going to go into a little more detail what I mean about that. But this is a key gap where Ember lacks clear implementation-independent semantics, a place where we have fallen into the implementer's trap. So as an example, here's two JavaScript files. And does anybody know what this code should do? What? It should fail. It's not valid. This is not valid JavaScript, right? It's actually supposed to crash. It's not supposed to be valid JavaScript because the utilities thing doesn't have a default export, right? It's just exporting a named export, and that we're trying to consume it as a named export. This instead would be valid, or this instead would be valid, but the original was not supposed to work. Does anybody know what it does in Ember? It works, yeah. And that wasn't entirely by accident. It's historical, and it's about compatibility. But as soon as you try to enforce really strict spec semantics on Ember, you find cases like this in the wild. There's totally popular add-ons that had done this. So that's a real bug. It has really has happened in the wild. Thankfully, this kind of thing is easy to find statically and easy to fix. But there's another. I can give a different example, and it's the harder part of the problem. So these are examples of imports that you've probably seen in Ember apps, this kind of thing. You might have these all over the place. The question is, what do these mean? Like, what do they mean independent of the implementation? Unfortunately, what they mean is different in all four of these examples. They all mean something different. And unless you're very familiar with the implementation, you probably don't know what those things are. I'll probably even get it wrong if I try to tell you. But just for one example, the controller one here, that actually compiles down to not even an import at all. It just compiles to a global. The Glimmer component one is actually a real module import. The QUnit one is actually falling down to a global again, but from a different source, from a different package that doesn't even QUnit. And so basically, we don't need to, let's not actually worry about what they mean because that's confusing. This part of the import statement that I've highlighted in green is the ECMA spec calls it the module specifier. And this is the part where we don't have clear meanings. Now, the good news here is that we're not violating the spec, the letter of the spec, because it doesn't have an opinion about what module specifiers are supposed to mean. JavaScript doesn't actually care what these mean. It leaves that up to the host environment, meaning it's up to browsers to decide what it means, or it's up to Node to decide what it means. So we aren't violating the letter of the spec by not having a clear standard here. But the bad news is we are kind of violating the spirit of the spec. What I mean by that is, let's look at how modules are designed. So here's two examples of things that are not valid JavaScript. Right? Trying to use something dynamic inside the module specifier is just a syntax error. And trying to use an import statement that's not at the top level of your module, if it's nested inside of something, that's also a syntax error. Why are these things not allowed? Right? The answer comes back to our definitions of static and dynamic knowledge. These examples would require dynamic knowledge to know what's going on. But the module spec was defined very carefully to be static. Here's another example. If you run the code in app.js here, what prints? Right? The answer is that hi prints first. Right? It doesn't print before hi after. It prints hi before after. Right? And the reason is the import statements are really not like executable code that goes in line. They're very much declarative, static declarations that this module must run before my own module. So these are just examples of why everything about import is designed to be static. And our semantics are not static. Right? So it's a mismatch. And this is why I say we violate the spirit of the spec by not taking advantage of this capability. Instead, our implementation of module specifiers is very implementation defined, and it's so implementation defined that you can't really know the answers till runtime. At build time, we really don't even know what all these things mean. So we have here an instance of the implementer's trap. We think about these too much by knowing how they really work, and not enough of having a clear standard for what they should mean. I will point out that all these cases that I showed that don't work with import do work with dynamic import, which is import with parentheses, which is a powerful feature that is part of JavaScript now, that lets you do all the things that you can't do with the static import. It's specifically designed for that case. So a pause for another bonus fact. Speaking of modules, let's talk about lunar modules. From my house, you could take a 5-kilometer bike ride down what is the busiest commuter bikeway in the region, and end up at Draper Laboratory. So Draper Laboratory was formerly the MIT Instrumentation Lab. It split off from MIT in the 70s after student anti-war protests, because it turns out the lab does a lot of research for the US military. It did then, and it still does. But one of the coolest things to come out of Draper Laboratory was the Apollo guidance computer. It was created there, and that computer had 3.8 kilobytes of RAM, 69 kilobytes of ROM for storing its programs, but it controlled all the spacecraft that went to the moon. This is a close-up of what the 3 kilobytes of magnetic core memory RAM would have looked like. So you're actually seeing tiny iron rings that are hand-woven, you might even say hand-embroidered, onto a network of very fine wires. Each ring can be magnetized clockwise or counterclockwise, and so you're looking at the actual bits there. And people would have stitched by hand all 3,000 bits. The computer was programmed directly in assembly language, but it did have a built-in virtual machine, just like GlimmerVM, for expanding the set of operations that programmers could use. And that helped them cram their programs into that 69 kilobytes. So this is the part of the talk where we stop defining the problem and start talking about solutions. And I said the part of the problem is we don't have a clear spec for what these things mean. So the first part of the solution is writing a spec. And the first part of that spec is this RFC that's titled V2 add-on format that's published now. It's a very long RFC. I didn't quite realize while I was writing it. Some friends printed it out for me, and it's like 10 feet long. But it solves these problems, and I'm not going to spend a lot of this time on this talk going into how it solves those problems. But at a high level, it certainly does address the things we talked about. It creates a standard for what those module specifiers should mean that has one constant meaning, that is static meaning. And on top of that, it does a bunch of other things and cleans up a bunch of loose ends around what packages an Ember can do. And it's titled add-on format. And so you might think it's only a thing about add-ons and it doesn't touch the core experience of writing applications. But really, add-ons are the hard case for our build system and in general for coordinating code between many people. Right? Add-ons tend to come across organizational boundaries. And so having very clear specs for what they can do in terms of interface is like the most pressing thing to solve first. And once you make a good format for what packages can do, apps are just another kind of package. Right? So this is really talking about a clear standard for what code means in Ember and how you express it. In addition to clarifying the module specifier stuff, for example, it standardizes what are the kind of hooks that add-ons can use at build time. It standardizes what language Ember packages are supposed to be written in. And what I mean by that is like saying very precisely what JavaScript features are supposed to be in there, which ones are not. Today, there actually is no standard. Today, the only standard is when an add-on is published and you go to use it, we just call some code in the add-on, and it's supposed to spit out JavaScript back at us. And it can do that however it wants. And so its own code could come from anywhere. It could be generated on the fly. It could be compiled from a totally different language. It could use non-standard JavaScript features and compile them on the fly. All of that means that you can't necessarily know where the code is coming from. Your editor can't tell. TypeScript can't tell. Linters can't tell. Optimizers can't tell. And so that's the kind of problem we're trying to solve by standardizing what goes in these packages, what language it's written in. So a lot of it takes away capabilities from the add-ons, and it tries to reintroduce them in ways that are static and analyzable and safe. So for example, you can still author add-ons in any language you want. You just have to compile it before you publish to NPM. So having a spec is great. A new spec is great. That solves the problem of not having a spec. But what good is that if all of our code that exists doesn't follow the spec? So that takes us to Embroider and the implementation of it and how it works. So Embroider is a multi-stage compiler. And what I mean by a multi-stage compiler is splitting the work of compilation down so that instead of going all the way from your source language to your destination language, you stop at some intermediate languages along the way. Now that might sound more complicated, but it turns out to have a couple very powerful properties. And so it's a common thing you see in compilers. Here's an example of the Rust compiler. So don't worry, this part won't be on your homework. But Rust, the Rust that you write as a human is the input language here. And it goes through the Rust compiler's first stage to come out into a language called high-level intermediate representation. And that first pass cleans up a bunch of human niceties out of the language so that the future stages of the compiler don't need to worry about that complexity. Then the next stage of the compiler takes that down to medium-level intermediate representation, which is able to do a much more powerful set of transformations on the code. And then that sets up things and provides enough information so that the third stage of the compiler can do the work to take that representation and convert it to a format called LLVM intermediate representation. So LLVM, low-level virtual machine, is a separate project. It has nothing to do with Rust. LLVM is underneath many compilers. It's used to compile many languages. And so it's a project that knows how to go from this standard LLVM IR language down to machine code on a whole variety of different kinds of hardware. Right? So this example is useful because it illustrates the two powerful things about multi-stage compilers. The first is that your early stages can do a lot of work to set things up so that the later stages can take more things for granted. They can have more information. They can assume certain invariants because the early stages took care of that. And so it makes the later stages more powerful. It gives them more information, and it gives them more simplicity. The second thing that's powerful here is this idea that you don't need to compile all the way to your final target language. You just have to compile far enough to get to a good standard that has good standard shared support to get the rest of the way. Right? And we use both these capabilities in Embroider. So in the Embroider architecture, we have 3 stages. We have a compatibility stage that takes in the Ember app and add-ons that you have today, all the existing code you've got. Right? And so And as output, it produces the new style packages that follow the new style spec. You can imagine that, therefore, the hardest work in Embroider is that stage, because that's the one that has to figure out all the current possibilities of what packages can do today and try to standardize them. Right? And so then the second stage is able to basically live in the future. It sees its input as things that are already in the nice new world, right? So we get to implement the core semantics of how Ember is supposed to be built, assuming these pleasant v2 standard packages as input. And then as output, that stage produces plain JavaScript, CSS, and HTML. And what I mean by plain is it doesn't need to know at that point all of the Ember-specific conventions are expressed explicitly in the code. So that leaves you to the third stage where a standard tool that doesn't even have to know much about Ember can take that code the rest of the way to a browser-optimized or node-optimized for fast boot payload. And so that's just like how Rust uses LLVM IR, right? We can compile our Ember app's own semantics, our own conventions, down to a much more explicit, that you wouldn't want to write by hand, but clear representation just using the specs of HTML, JavaScript, CSS to represent exactly what an Ember app is. And so what's great about that is that now we can use a standard third stage, which the first example of it is implemented with Webpack, but because it's a standard input, we have the power in the future to swap that out. We could try, if somebody comes around and you could try Parcel instead, or if somebody writes a future one that's fast and great and optimizes better, we'll have the capability of using it. So let's talk a little bit more about what goes on in the stages. So in the compatibility stage, stage 1, this is where all the custom things that add-ons are trying to do, custom broccoli trees that they provide, custom hooks and things like that, all have to run here because by the output of this, we want all of our packages to be just a bunch of files sitting on disk, just a bunch of plain old node modules. And we move files around so that they always match their import paths, right? In the v2 spec, if you say you're importing something from QUnit, it's going to come from actual package QUnit, where Node expects to find it. Right? We also spend a bunch of effort recapturing modules that try to escape their packages. What I mean by this is there's a lot of cases where add-ons let you import from some package name that isn't a real package or isn't their package. And so that's the thing. That's the thing that the new spec doesn't allow, because we really need to know where every file comes from. You're only allowed a package is only allowed to provide files under its own namespace. It's very rude to invade other people's namespaces. So we spend a bunch of effort finding and capturing those things and moving them back into the packages where they belong and rewriting imports to match. We apply any custom preprocessing at this stage. So if an add-on is shipping with custom Babel plugins that only run in a particular version of Babel, or custom HTML, HBS transforms, those custom transforms run here, because in the new world, everything's supposed to be in standard one language by the time it gets to stage 2. Right? So we're going to compile away all of that. And lastly, we generate things like a synthesized vendor package, which is just a place to basically be the kind of compatibility dumping ground of files that today in Ember apps are allowed to collide between packages. And for compatibility, you actually want them to. So we basically find ways to represent all the classic behaviors as valid v2 packages that fit in the v2 spec. And again, the reason for this is we don't want a whole lot of special cases in stage 2. We want stage 2 to see this new, perfect, nice system. So we find ways to encapsulate all the complexity of existing packages as these nice new to v2 packages. Stage 2 is the core, and it's called that because this is really where we implement what does it mean to be an Ember app, how do Ember apps work. This is the part that understands things like what is an engine, what is a lazy engine versus an eager engine, what's a route, and when you load a route, what files do you need? So this is the part that understands how Ember apps are put together, and it can take those nice conventions that we're able to. We get lots of developer productivity out of having conventions, knowing where things go, knowing what they're named, knowing that when I load this route, I'm going to get this template. The core understands all those conventions and takes them and translates them longhand into JavaScript. Right? So for example, it's going to actually synthesize a JavaScript file that's an entry point for your application that will explicitly have import statements for all the files that we know are needed to boot your application. It's going to synthesize separate entry points for engines so that they can be loaded as chunks. It's going to actually resolve components and helpers in your templates and emit import statements into those compiled modules, so that when a particular template depends on a particular component, which depends on another particular component, that dependency graph is now legible to the third stage before we get there, because there's explicit import statements for it all. And the reason we can resolve all those components and helpers at this stage, if you've tried to solve that problem in builds today without all of this infrastructure behind you, you realize that it's hard to bordering on impossible to be sure and resolve all those things at build time. The reason we can do it is because stage 1 already did all of the complex stuff for us. It already ran all the custom code. It moved all the files around so that they will be in reliable places. So that's why core is able to do this kind of thing in a relatively straightforward way that was before very difficult. And that's just the power of multi-stage compilation. And finally, core uses the JavaScript dynamic import to express potential split points. So things like a lazy engine, we can express what that means in just JavaScript by having a JavaScript entry file that is the entry point to the engine and dynamic import it into the application. And that makes it clear to any system that understands JavaScript, here's some code that I might need to load, but I'm not going to load it yet. Compile it for me. Make sure that it's valid and preserve the semantics. And so that lets us do things like have splitting on routes and splitting on engines and things like that. Stage 3 is optimization. As I said, right now, the one we have is implemented on Webpack. That's got good and bad. It's very good because it is so popular, other things in the ecosystem tend to work well with it, or because if they didn't, they already got a bug from somebody to make it work with Webpack. Because we've standardized the input to this stage as just spec compliant things, we basically don't want to tie into one particular tool here. It's great to be able to use the best of what the broader world is investing in. All the effort that other communities put into tooling is stuff that we can decide to absorb and take advantage of, and we'll retain that flexibility in the future. And so one thing we do at this stage is give it total freedom to decide how to take our application and actually deliver it to browsers. What specific JavaScript files it will write to put on your web server, we leave it as implementation detail. It might choose to split your app into 3 files. It might choose to split your app into 40 files. we don't necessarily care. We just give it the freedom to optimize and deliver it whatever way seems best. And so, of course, as an application developer, if you needed to tune those things, of course, you'd be able to. But the idea is that Embroider as a system continues to work just fine, no matter what optimization algorithm or settings an app needs or chooses to use. Bonus fact, this is my bike. So my bicycle is Dutch, despite me being very American. And people are sometimes surprised to see Dutch bikes in America. And it's true that in a lot of America you wouldn't, but Somerville is one of the best cycling cities in America. And I know that isn't saying that much to folks from Copenhagen or other great biking cities. But we've done a lot in the city to make it bike safe and bike friendly. And personal car use has fallen below 50% among residents of Somerville. Biking is up to almost 10% mode share. And activists and the city government are working really hard to keep pushing that higher and make us a more livable and green city that's safe for people walking and people biking. And one of the ways we do it is really by copying lessons from cities like Copenhagen, Utrecht, Amsterdam. There's an awful lot of attention from folks in my town on places like here. And being here has actually been giving me a bit of hope. I had hope already, but more hope, because we're actually copying all the individual elements pretty well already. We just have to do it more consistently and more scale it up, right? So it's going well. And we even have also 6 new light rail stations under construction in Somerville right now. We've taken away whole lanes from cars and dedicated them to bikes and buses. So that might seem downright un-American, but it's really just a return to our own history. My city was built around trains and streetcar lines. And in 1910, it was served. Somerville, all 10 square kilometers of it was served by 9 train stations. Right? It's very much in our bones and in our history to be a transit-oriented city, and so we're returning to that. And so I'm always happy to chat bikes and transit and green cities with anybody, because I geek out on all that stuff. So the benefits of Embroider, then summarized. We end up with a complete pull-based build system. And what I mean by that is, this is the area where people tend to use the term tree shaking. It's an okay term, but I actually think it's a little bit inaccurate for a system like this, because we don't first take all of the things, put them in your app, and then shake out the things you don't need. We just choose to never put them in the first place if you don't need them. Nothing gets into the build unless it's explicitly needed by something. Right? So that's why I mean, say, pull-based build. Your whole application is really just represented as a single JavaScript file, well, HTML actually, HTML entry point, and that has script tags that need JavaScript modules, and those modules need other modules, and etc. All right, on in, and so it's all pull-based. A second benefit is faster builds, and I've gotten some very wildly differing feedback actually already about the Embroider as it is today. It was great to hear from someone at the conference that their app builds 5 times faster with Embroider already than it does on standard. I wasn't expecting it to be that good yet. And on some apps, it just totally bugs where it's slower than standard Ember CLI. But our goal is it's definitely not slower. It's at least as fast with the full compatibility system turned on. And I expect it I expect it to settle down being faster, at least a little bit faster, with the full compatibility system. Without the full compatibility system, meaning as more and more of your add-ons ship natively in the V2 format, it gets dramatically faster. And this is really a consequence of having good static semantics. It means that you can answer a lot more questions more easily about the code. And so the whole build process can go faster. It needs to run a lot less custom things. Another benefit is that so a dynamic import is now allowed anywhere in your code, and it works. It's just JavaScript, right? It's legal JavaScript that has a very precise meaning. And so this is a very powerful low-level primitive for lazy loading things, splitting things. It's a thing that now you can just use anywhere in an Ember app if you wanted to. And so it gives us a powerful low-level primitive that is, it's something you won't necessarily have to use directly to get a lot of benefits, because we can do some of those for you. But if you need it, it's there, and you could build powerful systems on top of it. And it's also a safe thing to use in the sense that it's part of the ECMA spec, right? What it means is very clear. It's not going to change. Browsers themselves are implementing it, so it has a very fixed meaning. And so you can be confident that anything you implement using it is going to continue to work under future build systems, under future requirements. One of the things that we build on top of dynamic import is automated route-aware code splitting. So with using Embroider, you can already configure this route, and this route. Don't load them until people need them, right? And that will actually take care of not just the routes, of course, but all of the components and templates and libraries that they use, and et cetera. Allowing you to scale out Ember apps in a way horizontally as they add features without slowing them down, right? It's a nice feature to have. Today, to do that, you had to use a lazy engine, and lazy engines aren't really just for that. Engines are really useful for very large organizations where you're trying to keep two teams out of each other's way. And it's when it's really all one team working on the application, engines are not the right solution. And so having a much more lightweight way to split apps is very great. And another benefit here is being able to import anything directly from NPM, statically or dynamically. This is the thing you do get today already if you use Ember Auto Import, which I also made. Which is not a coincidence. Ember Auto Import really is basically a polyfill for a part of Embroider. The main difference being Auto Import only works for non-Ember packages. It doesn't really let you dynamically load or depend on Ember packages because of all of the things that like Embroider Stage 1 needs to do to really understand Ember packages. So Embroider can do that for any packages, including the Ember ones. So that's really nice. That lets you, it lets us integrate more closely with the rest of what's available on NPM, et cetera. And so, all of these benefits are one by one. Each of these benefits is maybe not super interesting in 2019. Like there's definitely other things out there that do these things. But I think what's really is powerful and exciting about these features is that these are features that we're bringing into big apps that were started before any of these features were really on anybody's radar, right? That's the power of being able to work together as a community, put in the effort to build things that last, come up with agreement and standards, and keep pushing forward together. So I'm really proud that our community's work makes this kind of project possible, right? Sure, it's great to be able to use a new feature that was only implemented in recent years, but if that doesn't come into old apps, that's not practical. I think we're a very practical community that knows how to keep moving forward together without doing giant rewrites, and I'm really happy about that. So I will end with comments on next steps here. I know the question on everybody's mind is, when do I get to use this? What do we do? So you can already try it. Everything is published. There's a README that explains how to try it in an application. Trying it out in your application is very safe and low risk kind of thing. And very specifically because we don't want to change the semantics of Ember apps, right? So you're never required to go rewrite parts of your application to use Embroider, at least certainly to try it out, right? So there's no big question of when you have to bet on switching to Embroider, because it's a thing you can implement as a feature flag and change 2 lines in your Ember CLI build file, and you'll use Embroider instead of the standard build pipeline. So it's cheap to try. Now that said, it's still unstable and early, and so I wouldn't go using it on your production app unless you're very brave or very foolhardy. But it is a great thing to, for example, if you're willing to help out and try it out. Maybe add it to your CI build matrix so you can tell us if it's going to build your app well. The path to stabilizing it and making it standard is really, the first thing is that RFC I mentioned. We need to get that standardized and merged. And I think the only thing we're waiting on there is attention from more people. Once Octane is really out the door, we'll get more attention from the community and from the core teams to hammer out the details of that new spec. Once we have that RFC merged, that lets us start publishing fixing add-ons that are out in the community to be natively Embroider compatible. There's a bunch of compatibility hacks in Embroider to make sure that you can work through things that are, basically any add-on that's out there, we can have hacks to make it work. But of course, to make it stable and reliable, we don't want hacks. We want to actually fix problems upstream. So we merge the RFC. That lets us begin to publish add-ons in the new formats. That's what's going to stabilize the whole ecosystem for us, so that you'll be able to use Embroider and feel confident that your add-on is going to keep working and not break. And so that puts us on the path of, adding a feature flag in Ember CLI that would just make it use Embroider instead of the existing build pipeline, and let people start using it, testing it for real, getting a few apps into production with it, getting a lot of good feedback. And there's probably a requirement for at least a couple more RFCs to hammer out some of the details of what the real experience for app developers is going to be. But basically we're well along our way of shipping this, similar to how we've shipped all the Octane features, right? We ship them piecemeal over time, where people who were excited about them could try them and begin using them in real applications. And only now, after having shipped those features over the course of a year plus, are we actually saying now it's like all really done, coherent, time for everybody to adopt, right? Embroider is going to have a similar thing. If you're excited about it, you're going to get to start using these features quite soon. And then over time, we're going to have it so polished that it'll just be a thing we turn on for everybody. So that is it. Thank you.